Hello and welcome to our talk. My name is Matt Gadd and I am a postdoctoral research assistant at the Oxford Robotics Institute. My other co-authors are Daniele De Martini, Paul Newman and Lars Kuntz from the ORI, as well as Letizia Maciegiani, who started this work with us at the University of Oxford, but is now at Aalborg University in Denmark. How does this research agenda fit into our history and future ambitions as an institute? Our institute, the Oxford Robotics Institute, put a driverless car on public roads in Oxford in a sort of European first in 2012 to 2013. And this was followed by a very public and popular robot car data set in 2015 to 2016, which some of the people in the room may have heard of and even used in their own research. Since then, I think since that time, there's been an explosion of self-driving companies emerging in the landscape in the United Kingdom and worldwide. And our focus and a big part of our messaging through all of that time was on dealing with adverse weather for robust self-driving. I mean, in amongst other things that we're focusing on, but this was a big part. Dealing with bad weather in computer vision models was a big part of our messaging. And at this stage, now, today in 2020, our thinking is a little bit more nuanced. And while we're still interested in robust sensing, we are increasingly interested in baking in introspective capabilities into our processing and how these insights into how algorithms are working and what the intelligent machine is sensing can be meaningfully communicated to a human stakeholder, human user, human occupant, etc. We believe this is a crucial prerequisite for building human trust in self-driving systems. So here are some example scenarios in plain English, kind of to warm us up during this talk. And they're all about the autonomous vehicle making intelligent choices for safety or performance reasons. We also want our AVs to have the ability to explain the reason that the choice has been made, even when that reason is not obvious for a human operator or a human occupant. So in the first example, faced with a flooded roadway, we expect the AV to explain the vehicle will take a route over an area of gravel. The route is slightly longer than the direct route, as there is a non-traversable body of water in the direction of the goal. And this is like a natural language statement of something we'd like the AV to achieve. But you can read through all three of these examples, and an example I've just discussed, that there's quite a lot of perception, performance assessment, and explanation, artificially intelligent capabilities going on there. And it's a fairly tall order, I think, considering where we are in the community. So we say, at least, for the AV to present this level of auditable behavior, we identify three research challenges that need to be solved. Firstly, as we've been talking about for years, we need sensors which are robust to environmental changes, but we also need algorithms which are robust to the same effects, either through hand design or through learning from real or synthesized data. And second, these algorithms need to be introspective enough to have some confidence in how they are performing and reliably detect when they are underperforming. And lastly, this confidence, as well as how the confidences for various subsystems influences decisions such as path planning or sensor scheduling, as two examples, is not complete if it cannot be communicated to a human in an appropriate way. And by appropriate here, I mean something different depending on the human we are talking to, whether for a researcher, developer, or designer, this might be fairly technical on a statistical or on a code basis. For a sort of passenger human occupant, this communication from the algorithm needs to be human friendly. So rational, reassuring, and above all, not technical. So our proposal kind of comes in two stages. We propose first what we think of and what we're proposing as a useful framework to address these research challenges. And we call this Sense, Assess, Explain, or SAX. Later, we will describe our particular interpretation of this SAX framework, or our, said another way, our particular instantiation of it. But for now, we can summarize our project scope as the vehicle explains at different levels of abstraction what it has sensed and assessed. Sensing we define probably uncontroversially as perceiving and interpreting the environment. And as a community developing robust, reliable autonomy, we need to go beyond the state of the art, all the way from a hardware level right up to the data science which we use to process the sensor data. And so we'll discuss the data set that we're collecting in a few minutes, but suffice it to say that we consider it particularly important in not just urban, but also mixed driving scenarios to understand driving surfaces. That's very important to us. And as always, resilience over short and long timescales to appearance change is very crucial. And finally, we also consider the use of non-onboard sensors such as weather services and satellites. And this is because we acknowledge that in a way, the world has already been quite comprehensively mapped. And with fast data connections, we may as well take advantage of that. The second part of our proposed framework is called assess. We can apply a bit of a synonym to this and call it introspection, which is a word I've mentioned a few times already in the last couple of minutes. And we want to know in this area of our research why a failure has occurred when the robot is performing a task with a sensor, such as localization with a camera. And we'd also like to be able to know in advance that a failure is likely to occur. Ideally, we could use this knowledge to build multi-sensor systems which never fail. We consider that this sort of assessment and introspection can only lead to increased environmental awareness. And if tied back into navigation and control, will adapt not only to the sensing prowess, but also the driving behavior of the vehicle towards ultimately greater safety. So the third part of our research agenda considers that the safe deployment of autonomous vehicles in real-world scenarios requires them to be accountable and trustworthy. So it's necessary to explore the impact of explanations that provide information about an autonomous vehicle's behavior. In essence, explaining what a vehicle has seen, done, and might do in a given scenario. And such explanations offer the potential to allow developers and regulators to assess the behavior, upholding accountability, and may also foster human trust. So this third pillar, explain, is a weirder one where we'd like the vehicle to explain in non-engineering and human terms what it has seen and how that has influenced its decision-making. For example, the vehicle should be able to explain that it took a steeper route to its goal because the flatter route was covered in water and was therefore possibly more treacherous. So far we've discussed the broad view of the SAX approach in general, our framework, our proposed framework. And we'll now talk about our interpretation of it, or our particular instantiation of it that we're putting forward simultaneously. In the first pillar of this agenda, sense, we're interested in more robust sensing with traditionally exploited sensors such as cameras and lasers, as always. But we're also interested in sensors such as radar, which are more robust to poor lighting and weather. We're even interested in more unusual sensors such as audio, and even sensors which are not on board, like satellite imagery. Because localization is such a crucial enabling factor for motion control when deploying autonomous systems, an important objective in our work is building localization systems which understand how well they are performing. We'd ultimately like this to be running for multiple localization systems, for example, for a radar system, and for a camera system, and for a LiDAR system in parallel, which would allow us to intelligently fuse these localization sources and drop one if it starts behaving badly. Beyond localization, we can consider more general scene understanding, such as through semantic segmentation of camera images, which is shown on this slide. A typical approach, neural networks, an increasingly popular approach, they're inherently deterministic algorithms, and if not trained properly, they can easily lead to overconfident results, even in the incorrect predictions. So here we want to estimate the confidence of the models and to not even try to segment parts of the scene where the model is unconfident that it will perform well. So we believe that this will improve segmentation performance in the confidence regions simultaneously. And if we have a confidence estimate of the neural network, we can use this empirical evidence to help define regulations for where it is acceptable and safe to deploy AI systems as another output of this investigation. So this explanatory thread, the third part of our pillar and our interpretation of it, lies at the heart of our assurance and trust research agenda. We feel that it's sorely lacking in much of the autonomous vehicle research endeavor. However, based on great workshops such as this one, the narrative is clearly changing. We have to be able to offer users pathways to trust and assurance of what machines are doing and why. And they have to be able to explain these machines, almost justify what they are doing, what they see, what it means, and what they plan to do next and why. So we show here the platform we use for the project. It's a Jaguar Land Rover, heavily modified to include a full sensor suite, as well as high-end computational capabilities. From the top, we can see the radar sensor and the 3D LiDAR, and both of them can scan the environment around the car with a 360-degree field of view. And while the radar, as we said, is one of the main sensors under investigation, 3D LiDAR is anyway very useful for baseline definition or weakly supervised training of radar models, as well as just giving us very good high definition surveys or HD maps of the environments that we're jaunting around in. Next is the GPS INS. While we advocate the use of perceptual sensors over GPS for autonomy, and we have done for many years, this sort of sensor is useful in conjunction with external services such as weather services, not to mention useful in providing localization and odometry ground truth in certain circumstances. And although not visible here, we installed a reflective prism that can be used to survey the relative position with respect to a Leica laser pointer. And such a surveying tool, normally used in constructions, can give very accurate position estimates on the order of millimeters at up to more than a kilometer of range. So we can track this thing while it's very far away. Yeah, cameras are of course super popular for autonomous vehicle research. And so we've equipped our vehicle with wide and narrow baseline stereo cameras facing in the direction of travel, as well as monocular cameras providing a 360-degree view around the vehicle. Although not directly used in this project, our car is equipped with 2D LiDARs that cover the whole perimeter of the platform and could feasibly be used and have been used in the past by us as part of a software and hardware safety curtain under autonomous conditions. And finally, we mount a microphone within the wheel arch at each of the four corners of the vehicle to get them as close to the driving surface as possible, where we think that interesting noises, interesting sounds will come from. So we're in the midst of a trial program to take this vehicle and sensor suite out for data collection. The thinking behind the design of our data set on our side was that we have previously captured all weathers in one place, by which I'm referring to the Oxford robot car data set. And at this time, we'd like to really capture all weathers in all places. So we're going all over the United Kingdom. A little more formally, our focus for data capture revolves around unusual sensing modalities, mixed driving surfaces, and adverse weather conditions. And specifically, we want to complete thousands of kilometers of driving in both rural and urban England with our now Range Rover robot car, and capture data in a wide set of atmospheric and illumination conditions while traversing a variety of surfaces, including highways, country lanes, mud paths, cobblestone streets. So we're really getting out there. This trial program was well underway in early 2020 before it was disrupted by the global COVID-19 pandemic. And we're starting it up again now. In fact, the first trial since March is happening while I am preparing this presentation. And the first area we have gone to record data is an adventure driving course called Experience the Country, which is situated just outside Milton Keynes in South England. And here you can see footage from some of the medium and more challenging driving conditions. We've learned a lot with these early trials, specifically around capturing ground truth motion with our Leica tracker, and also due to the conversations we've had with the expert off-road driver that we've employed while in the driving cabin with them. And so we're really hoping to include this sort of human commentary in some way in the dataset release as part of the explanatory thread of our research agenda. So in the last part of the talk, I want to talk about our recent publication record around the SAX agenda and ongoing work, as well as a few open questions. So estimating how a robot is moving is essential for building maps and controlling the motion of a robot when it drives autonomously. We've shown that the radar can rival and even outperform cameras at this task, and we've built performance assessment capabilities into our existing radar odometry pipeline. Figuring out the location of the vehicle in those maps is also essential for autonomous operation. We've shown a real benefit from radar in being able to localize at night or under conditions of heavy rain against maps which are collected during the day. We also have to recognize that the world is already virtually mapped, as I mentioned earlier, for example, by Google Maps Outdoors. And so we've exploited these digital representations that are ubiquitously available, but underutilized in conjunction with onboard sensors. And so in doing so, we've built cross-modal radar satellite learned localization models, which are strongly as well as self-supervised. Finally, understanding the location and category of each object in the scene is very important to safety. On the top is some of the work we've done identifying the safe gravel paths which a robot should drive on in the university parks using radar and audio. On the bottom, we did important work understanding the entire scene and its contents as scanned by radar, otherwise known as semantic segmentation. Autonomous vehicles require an accurate and adequate representation of their environment for decision-making and planning in real-world driving scenarios. I'm sure you'll agree. And while deep learning models have come a long way providing accurate semantic segmentation of scenes, they are still limited to pixel-wise outputs and do not naturally support high-level reasoning and planning methods that are required for complex road maneuvers. In contrast, in this work we've published, we're interested in an hierarchical graph-based representation, which we call a scene graph, which is reconstructed from a partial pixel-wise segmentation of an image, and which can be linked to domain knowledge and AI reasoning techniques. So in this work, we investigated learning and inference methods which can identify causal links between semantic scene representations and human driving actions. And by generating an interpretable representation of road scenes and linking them to driving actions, we believe that this approach provided a vital step towards explainable and auditable models for planning and decision-making in the context of autonomous driving. We've also recently engaged in a user study where we examined the effectiveness of causal and non-causal explanations provided by an autonomous vehicle. We quantitatively evaluated explanations using subjective goodness and objective performance measures. We also conducted qualitative analysis to discuss the impact of explanations on trust. And our results show that causal explanations improve task performance when assessing driving events, including accountability, but do not increase trust. And additional measures for building trust in autonomous vehicles, we conclude, are therefore necessary. And with that, I will close this presentation. From all of us at the ORI, thank you for listening. We hope that you enjoy the rest of your virtual Intelligent Vehicles Symposium. Please do get in touch with us either online in one of the sessions or offline via email or Twitter if you have any questions or would just like to chat about our work. Thank you.